Singh.
Um, Good evening to all of you. PAC is honored to host a lecture by Dr. Ashmeet Singh as part of Cosmic Quest 2026. Dr. Ashmeet Singh is an alumnus of IIT Roorkee and a former PAC secretary. He is currently an assistant professor at IIT Delhi, having worked at various institutions like Caltech, NASA Jet Propulsion Laboratory, and Whitman College. His current work includes solving questions relating to cosmology, quantum mechanics, and gravity. And on behalf of PAC, I thank Dr. Singh for accepting to this talk, and I request him to take over to the talk.
So, thank you all first of all for having me here. I must say, if you have known me a little longer, you will realize that my smile for the last 2 days has been the biggest it's been for quite some time now. So coming back to Roorkee is always coming home and seeing you all. It's really fantastic. So thank you. Okay, so I titled my talk as Questioning the Obvious. It's going to be a little bit of a weird kind of a talk, and hopefully I land my message to all of you in some relevant fashion, hopefully. But I kind of want to start with a story, and I want to take you back 15 years ago when I was a first year student myself in the 5-year physics curriculum that we had at that time. And as a first year student, I had just joined the so-called stargazing section. There was no PAC back in the day, there was no physics astronomy club, there was just the stargazing section in the hobbies club. And to be very honest, and very blunt rather, the stargazing section was seen as one of the more dull clubs on campus. People would join stargazing because अरे उसमें अच्छी गेड़ आ जाएगा, रस्सी लग जाएगी, you will be good with that. So people would come to stargazing to do just this. When I joined, there was a little confluence of some sorts where a few of us who were really, really passionate about astronomy got that together. And we asked a very simple question: what can we do with the stargazing section that would really bring it out of the oblivion and really kind of bring it out to the campus, have some events, get that electricity about astronomy out to everyone on campus, basically. So that's where we asked this question: what can we really do? And that's where Cosmic Voyage actually started back in the day. So 2011, we did our first ever iteration of Cosmic Voyage in collaboration with this group called Interactive Learning. They didn't survive that long, I believe, but we did. So I'm really glad to see that. And over the next few years, Cosmic Voyage became stronger and stronger, and we gradually expanded our event base, our people base, and I'm really happy to kind of come back. It's like a full life circle moment for me. So I'm really happy to be here. I must also mention, not to sound narcissistic, but the term Cosmic Voyage is also what I coined back in the day, so this is again quite special for me. Okay, so this talk that I want to present to you, it's a little of everything in some sense. I was thinking about what should I want to convey to you, and I must say I have given many research talks, I have given many lectures in classes, I have made many YouTube videos, I have also consulted for Veritasium per se. But this crowd is really special to me. This crowd is close to my heart. And I wanted to kind of tell you something which is personal. Because you all inherited something that we made about 15 years ago. Sitting in our hostels, with almost no budget, surviving on Maggie and Oreo shakes. That's what really happened, and this is the outcome of that. So what I was thinking was, what have I learned in the last 15 years that I can convey to a younger self of mine who was sitting here many, many years ago? And to that person, I basically want to talk about how to experience physics and astronomy in a way that you feel that you kind of keep that childish curiosity inside you alive, basically. I want to add that the way we do physics nowadays, the way the art is practiced, the way we do physics, the way we make career out of it, the way we publish and whatnot, you often tend to forget as to why you started in the first place. And that is really, really important for me, I believe. So I kind of want to question as to how can we make our journeys in a way which is connected to the very, very fundamental core, yet doing something interesting out of it. So I will try to kind of connect different dots over here. and talk about across my journey starting at IIT Roorkee, where I got a lot from this place. I went to multiple places, worked on multiple different topics, but certain kind of the style of my questions has remained somewhat invariant. What has that style been, and what have I learned from it? That's what I want to kind of convey to you today. So, in some sense, this talk is an amalgamation of various different things. It's going to be some personal reflection stories about what I have done across my 15 years, some lessons I've learned along the way since I left IIT Roorkee, and also I'll try to infuse some what I think is interesting physics along the way, hopefully as well. But I first want to start by questioning the obvious, and I want to start talking about the role of community in physics. I believe very strongly that we are all here today because we share a common love for the sciences, for physics, for astronomy. Right? And often we believe that physics is a science which is done sitting in a corner in a room, scribbling equations, or working in a clean lab with some very fancy equipment. But often the passion starts in places like these, where people get together and they ask the right kind of questions together without judgment. So taking you back, these are some glimpses from the early cosmic voyages. And what we really had was just people coming together for some very, very basic, for some very, very interesting community building exercises. How can we find the Earth's radius by measuring the shadow of the sun, for example? Simple lectures, just discussing what we could do as a group together. And that has really changed how we think about sciences and physics as a whole. So people coming together, I think it's a very, very big resource that we have. So your friends, your peers that you have here, I think are a very special bunch. So hang on to them, and you can actually do some wonders with this. I also want to mention the planetarium that we used to have back in the day, which was built. I hope that that will come up again soon. So that's on my list. Yeah. Okay. So next thing I want to talk about is as young students trying to get into research, you often ask the question, where do I start? I often get questions from students in emails who come and talk to me that I don't know where to begin. And the question always is, either I want to start with something super, super fancy sounding. I want to work on ABS CFT. I want to work on black hole thermodynamics. You want to work on the cutting edge right from the start, right? Or you feel that what is available out there is actually too difficult and I can't do it. Or you might feel I should upskill myself and maybe learn some AI tools and make some money out of it. So this seems to be the consensus of how people are thinking about getting into research, getting into science nowadays. What I want to do is maybe convince you a little bit that when you see a problem, problems are there everywhere around us that can be tackled. And you should try and tackle them even though something better, something more fancy, something more sophisticated might exist. But don't let that stop you from trying something yourself. The pleasure of trying some equations, some ideas yourself, regardless of what that means, is something really, really amazing. I'll give you an example. So back in 2011, I went to Ayuka for a summer internship. And I was thrust away to the library, given a book to read, and I was asked to just think about something called the Sunyaev-Zeldovich effect, which is basically saying if a galaxy cluster has certain thermal electrons, certain thermal neutrons, and cosmic microwave photons coming from the background, they get upscattered, they gain energy when they inverse Compton scatter of these thermal particles in the galaxy cluster. I was in the library for 1 month just reading about this. There was no agenda, there was nothing to be gained as such over here. What bothered me was galaxy clusters are pretty hot objects. On average, every galaxy cluster of a big size is about 10 to the 9 Kelvin of temperature and order. And people, what they do is they often try to use a distribution of velocities of the particles in that particular galaxy cluster. I was a little worried about this. I felt if it's so hot, particles are going to be so energetic that some particles might go beyond the speed of light and they might violate special relativity. A simple calculation, if you do it, what you find is that about 3% particles actually end up lying beyond the value of the speed of light. Now, this bothered me a lot. How are we able to use something so standard, something so accepted, Maxwell-Boltzmann distribution, and applying it to these gigantic cosmological entities and not even worrying about it? I asked my mentors, my faculty, and other people. The answers I got was, this is how it's done, or it's too difficult with the real stuff. Because a real answer exists, something called the Maxwell-Chapler distribution. It involved tensors, It involved tensors and some things I had no idea what they were as a first year student. What I wanted to do was, I wanted to take whatever I knew of relativity, basic four vectors, basic relativistic forces, and try something for myself. Did not matter whether it would lead somewhere, a publication, a grant, a conference, did not matter. What mattered was I had a question and I want to try solving it, even though something better was out there. Don't let that stop you. That's what I wanted to say here first. I tried it out, something basic, just kind of playing around with the math, and something interesting did turn out of it. I found a new distribution which does match Maxwell-Boltzmann for low temperatures, but gives something different at high temperatures, which was still compliant with special relativity, for example. Now, again, this might not break the path, but for an undergraduate to understand this, I think is pretty darn interesting. Yeah. This is not where it all stops. To be able to get this out there, I also had to weather through a lot of struggles figuring out how to publish a paper. How do you write a paper? How do you make it clean enough to understand? Across multiple different years, it took me almost 2 years to figure out how to get this paper out there. And this was my first ever publication, which I wrote as a single author when I was back in my undergrad days. Only because I wanted to toy with a little bit of physics, right? So take this in mind that in your everyday classes, in your everyday learnings, there are many such questions hanging around there, waiting to be asked. Don't wait until you get to the very forefront of physics. Start with what you know, and you never know what might surprise you, right? So keep this in mind, I would say. I also want to mention, you might say, that was, statistical mechanics, that was relativity. Of course, there is something interesting going over there. I do want to add, sometimes you find physics even in the everyday mundane life that you had. So around 2013, I was in my third year at that time, and I was a little disheartened for some personal reasons. And I was going on a bus journey from here to a town in the Himalayas. And on that bus journey, I was just sitting and watching the grid of trees planted along the highway. Have you all noticed there are like these trees planted in like a grid-like pattern? And I was sitting and just watching these trees go by. And as they would go by, depending on your angle of viewing, certain trees would line up at certain angles. Sometimes they would look like complete utter chaos. And I asked myself, can I model this? No one asked me to. There was no publication waiting here for me. There was no grant waiting here for me. It was just, I wanted to try it out. Yeah. I came back and I literally, in my Govind Bhavan hostel room, I got a piece of thermocol and I got matchsticks and I made a little real life model, like see how it would look like. And once I had a feeling for it, I wrote down the math behind it. I tried to basically use my basic awareness of what I know about Dirac delta functions, basic trigonometry, and try to make a model for how the coverage fraction would change as a function of the angle. Again, nothing big here, just to try it out and see what might come out. Along that scribbles, along those, why not kind of questions, I ended up also coming up with a method that we could use this simple projection to find out something about the grid as a way of data extraction. It got published in European Journal of Physics, again, one of my papers back in my undergrad days, not out of a big project, not a big collaboration, just a question that I wanted to ask because I was curious and I wanted to play with something. Then I want to talk to you about something which is also important, is the friends that you meet here and what they end up doing in terms of your physics journeys. So I was a physics student, and one of my friends, Aditya Pandey, he's a civil engineer. So this gentleman, he was doing his PhD at University of Illinois, and he worked on something very, very far from physics. He worked on natural hazards, and he worked on societal risk management as to how, let's say, if you have an earthquake, how should you best design cities to be able to be most resilient to natural hazards? So Pandey and I, we would hang out quite a bit back in the US. And we were sitting, and as PhDs have it, there are stretches of times when you are just dull and life is hard, you're working through things. And he and I were hanging out together, and he asked me a question. I asked him, what are you doing? And he told me this. He gave me this example. He said, imagine, there's an earthquake in a city. And the city has a certain pipeline of, let's say, water network, the gas network, whatever that might be. Now the earthquake comes and it ends up damaging the pipeline network of the city. So on the right, you are seeing a simulation of an earthquake in Tennessee, where on the right-hand side, different blocks tell you how many cracks happened in the pipeline network per unit area. Okay? So the question is that they wanted to ask, Given the observed data of pipeline damage, can you go and reconstruct? Can you go and infer the most likely or the average earthquake scenario that might have caused it? It's an inversion problem, it's a reverse problem that you want to do. But the issue is, you are trying to basically find out an infinite number of unknowns from a finite number of data points. It's a mathematically ill-defined problem, but they want to do it anyways. It's a basic classical field theory question of trying to inverse something from a given amount of data. What they do is, they basically talk about, since you can't exactly find the earthquake, what you do is, you go probabilistic. And to be a good probabilist, you go Bayesian. I hope you all know Bayes' theorem, right? Given certain data, what can you say about the signal? So the hypothesis is, given the data, signal depends on the likelihood, which is the data given the signal, times the prior information as to what you know about the earthquake. This hopefully should look straightforward mathematics from your JE days, I would imagine.
So this
जी.
at the
Mhm.
Bayesian technique where if you have a very small data, you can generate more data.
By using the correlations in the data.
Exactly.
Absolutely. That's what we leverage.
That is first used in the Palentine paleo DNA technique,
Archaeology
where the
technique.
sample is almost infinitely small because of 100 million. Sorry, don't take it as
Not at all.
we are discussing. So through Bayesian technique, they generate large number of DNA sample. From there, they can
They can do a lot from there. Exactly. So what they would do is exactly this. They would try to run some approximations with Gaussian distributions. Because Gaussian bells are very familiar to work with, they're easy, and they're everywhere around us, the central limit theorem. So they are nice. So Gaussian inference is actually easy, and we can use this. But the thing is, nature is actually a little bit skewed. And for real life data, you have high dimensional distributions, you have non-Gaussian distributions, and they are highly correlated. And to solve this is actually a mathematically very, very challenging problem. So what happens is, the math for the non-Gaussian case is actually really hard. And by really hard, I mean impossibly hard. There are no known solutions to this problem. You start with the Bayes' theorem, you try to define a so-called partition function by integrating over all possibilities, and then you want to see how can you find the average of what is possible. So you do this, but again, sadly so, there are no known general solutions. So what people do is, my friend Pandey, they would run something called Markov chain Monte Carlo methods, these MCMC methods, where on a computer, you could run random simulations in a certain technique, and by that sampling, you can tell something about what's going on underlying in the underlying physics. But the thing is, these MCMC things are amazing, but they take a lot of time to converge. You don't even know if they've converged very well. It's a pain, to be very honest. Physics comes to the rescue. In 2013, I went to Germany to Max Planck Astrophysics for one of my internships. I was working on radio astronomy. Nothing came out of it, other than the fact that my group was working on something called information field theory, where they were using ideas from information theory to try to reconstruct signals in cosmology. I was not mature enough to understand what they were doing, but I picked up some words. I heard the word partition function, Hamiltonian, something along the way. Talking with Pandey, we made the connection that what could be done, Bayesian inference of fields coming from data for civil engineering, you could actually map it back to statistical physics. The Gibbs partition function, you might have heard in your basic physics classes, the probability of a certain state, if you will, goes as exponential of the negative energy of the state. If you don't know about this, it's okay, just think about it this way. For something which is highly stable, has a low energy, and low energy means stable, which means higher chance of occurring. So either the minus Hamiltonian, either the minus energy goes as lower energy, more chance of it happening. So you can actually make a one-to-one connection between Bayes' theorem and statistical Gibbs partition functions. And you can actually define something called a Hamiltonian function, an energy function for the earthquake scenario. And once we have the word Hamiltonian, physicists, are free to run around wild. We can do a bunch of amazing things with this. So what we were able to do was, we could unlock the entire machinery of so-called Feynman diagrams used in quantum field theory, where they look at perturbations over the free field, the Gaussian field. And now we could apply it to actually civil engineering problems, but coming inspired from physics. And this is a little slide from my Caltech days where they had an entire wall dedicated for finding diagrams. So anyways, so we were able to basically find a Hamiltonian for the earthquake signal and then run this very well-defined technique where every single additive correction could be written as well-known terms multiplied together in an analytically controllable way. What these terms are, don't worry about that, doesn't really matter right now, but it could be done. And we did it. And this is what we found. On the right-hand side, it's a reconstruction from this intensive computational Markov chain Monte Carlo. And on the left-hand side, it's what we did with our IFT techniques. And as you might see, the result is pretty much in good agreement. But the wonderful thing was, we were able to do it much faster, order of 1,000,000 times faster than what MCMC was able to do. Why? Because we were able to kind of use the correlations in the data to be able to understand how to infer the best things. What I want to kind of convey with this is, the friendships you make here today, you don't know where they're going to lead, right? So these conversations in the hallways, in the canteens, at night, just these chit chats, without judgment, without the pressure to perform, they really mean something substantial. And I have reaped those benefits and being where we currently are. So I really hope you also, kind of talk with each other much more. Okay, my next act in the talk is talking about rethinking the fundamentals. So I went to Caltech, and I had a choice at that time. I was offered a position to work with Sean Carroll for my PhD, and what Sean was working on was something which is very dangerous: quantum foundations. For some people, it is highly adventurous, it's deep stuff, it's meaningful stuff, it's visionary. But for some people, it's actually a little bit crackpot. So depending on who you talk to, that work is on the edge of what can be done with science. I had a choice. Did I want to work on these so-called foundational questions, or should I work for something a little bit more safe in physics? I must add over here, physics has two kinds of risks in some sense. Risk number one is that you go and work on a problem which no one really cares about. In my PhD, I have felt that many times, that what I'm doing, is it even worth it? Does anyone care? Will this even lead anywhere? That's a real risk. And let me tell you, going on the road less traveled is not always brave. It can be stubborn at times. And you can never be sure where it might lead. So never let you be like, oh, this is, road less traveled is going to be more fun. May not be fun. Things which are fashionable for a reason. But what's important is you ask yourselves the right questions genuinely. Because the other risk is, if you end up spending the intellectually most alive years of your life on something which you don't care about, you're working on someone else's problem, right? So I had to make a choice, and I was not sure what's going to happen. But something did work out. So I said yes to that position, and what follows is a little glimpse of what I have been doing for the last about 10 years. So typically, when we teach you quantum mechanics, what we do is, we start off with a very specific recipe. We start with the classical world. And by that I mean, we start with an understanding of what are particles, what are the fields, what is space-time, what is locality. And from that, we take the classical equations of motion. You might have heard the word Lagrangian, Euler-Lagrange differential equation. Start with F equals ma, if you will. You do second law. You have the classical dynamics. And then what you do is, you try and quantize that theory. You take the classical theory, and then you sprinkle quantum mechanics on top of it. By doing what? By mapping all the classical states to a so-called Hilbert space of quantum states, and by demanding that operators or let's say variables like position and momentum satisfy a certain commutation relationship, right? The Heisenberg commutation relationship. You demand this, and then you end up with a so-called quantum theory where you have a Hilbert space, you have a state living in the Hilbert space, which is evolving around the so-called Schrodinger equation. Yeah. This is the standard recipe of what we do in everyday process. Now, this has worked wonders for 3 of the 4 fundamental forces: electromagnetism, the strong force, and the weak force. We have been able to quantize them pretty successfully. The standard model is testament to that. But gravity has not been so successful to be able to quantize. And people often ask about why is that so? People refer to you to big words like string theory and renormalization and whatnot. Just think about simply, very simply. To try to understand gravity, you must understand what space-time means. Right? Einstein taught us space-time and its curvature is gravity. So you want to understand what does distance mean. And to get a meaning of distance, you must probe small lengths. If you probe small lengths, Heisenberg tells me delta x delta p is of the order of h bar. So the smaller you go in position, the more uncertainty you have in the momentum. More momentum kicks means more energy. And more energy means more back reaction in the space-time, and the length definition itself changes. So in some kind of a cyclic way, quantum and gravity are not made to work well together. There are other reasons also, but this is like my first year spiel to people who are not from physics also, I believe. Yeah. Okay. So there are some big questions to be asked. What is the nature of quantum nature of space-time and gravity? How does the classical world emerge from quantum mechanics? And finally, are there observable signatures for which we can actually go and probe our theories alongside it? So what we have been trying to do is, we are trying to flip the script, questioning the obvious again. Rather than canonically quantizing a classical theory, what we are trying to do is, we are trying to gravitize quantum mechanics. So we want to start with some fundamental abstract minimal quantum theory. And under the right kind of conditions, we expect the classical world to emerge from it. Now this is difficult because quantum theory by itself is actually pretty simple. It's literally one vector in a large dimensional vector space just rotating unitarily, that's it. Quantum becomes interesting, quantum becomes non-trivial when you divide the world into subsystems, into you and me and galaxies and particles. That's where quantum becomes non-trivial, because that's where you have things like interactions, entanglement, correlations. And how do you understand from these correlations, how can the classical world emerge around? That's the big question that we have been trying to ask for the last about 10 years. Can we flip the script, and from minimum quantum mechanics, can we emerge preferred classical structure? Can we emerge space? Can we emerge time? And can we emerge the universe we live? So I'll give you another glimpse of what we're trying to do over here. I'll talk a little bit about how these effects arise in cosmology, for example. To do so, I'll give you a 5-minute, not even a 5 minutes, 2-minute crash course on quantum field theory. So I know people here are from various different departments, various different years. So I'm not assuming you know much, just take the basics, that's what's important over here. So QFT, quantum field theory, is our best model for physics so far, but it does not include gravity in it so far. And here is the basic idea. You might have learned in your JEE days that for a relativistic particle, the energy depends on the momentum through the Einstein dispersion relation. E is p squared plus m squared. C is 1 for me. And then the de Broglie relationship tells me that there's a wave-matter duality. Every energy can be thought of as a frequency of the associated matter wave. And then for a given wavelength, you have the de Broglie momentum as well. Standard stuff that you learned. What this means, let's not get into that today, but this can be done. So basically what we're doing is, every single particle can be labeled by a momentum vector, right? How much momentum this particle has. And momentum in 3 dimensions will have 3 components, kx, ky, kz. We're living in k space. So if I can specify to you, how many number of particles have a given wave number k1 vector? How many particles n2 have the vector k2? And so on and so forth. I have specified to you the entire energy content of the universe, right? And then you might say, okay, if I know that, I can tell me how much energy is there in the universe. For a given energy, if there are n particles, just multiply n by the energy of per particle, you get the total energy. Right? Now this should look eerily familiar to many of you. The energy values are linearly spaced. You add more, you go up more. Yeah? This should remind you of the so-called quantum harmonic oscillator, whose energy states are like n plus half h bar omega. You add more particles, you go up the ladder. Yeah? So this is like a simple model, like putting the universe in a box, putting these standing waves, normal modes inside the box, and that's your done. So for us today, for the next 10 minutes, a quantum field theory is literally a collection of free quantum harmonic oscillators, one for every single momentum value. The occupation number, the n, tells me how many particles are associated with that particular momentum value. And what you do is, you go and you quantize it by imposing the canonical commutation relation between the field and its so-called canonical moment. Okay? So that's QFT for me. That is a bosonic QFT. Okay. Now the important thing is QFT, the Hilbert space, the space of all possibilities in quantum theory, is actually infinite dimensional. Now you might say, okay, I can maybe have arbitrarily long wavelengths across the universe. I can maybe have arbitrarily short wavelengths in the Planck scale maybe. But even if I put my theory on the lattice, so I have finite number of possible standing waves in there. Despite that, every single standing wave, the occupation number can go up to infinity. If you take in some quantum, you can apply the creation operator, A dagger, A dagger, A dagger, and keep going all the way up to infinity. No one can stop you. Yeah? So QFT, for a bosonic QFT, by that I mean these are harmonic oscillators, the Hilbert space is infinite dimensional. The other thing is, QFT, if you have a certain box size, like a gas, like a box of a gas, right? If I double the volume of the box, the entropy also becomes double, right? The number of possible microstates, the number of possibilities also doubles. So entropy in QFT is volume scaling. Double the volume, double the entropy. Okay. All right. So let me maybe skip this. But back in the 1970s, Stephen Hawking and Jacob Bekenstein, they taught us something about gravity, which is a little bit weird and counterintuitive to how this low energy universe works around us. What they said was, for black holes, the amount of entropy in a given black hole actually does not scale as the volume of the black hole, of the volume, the area of the region, but rather as the area of the region. That is weird for two reasons. Reason number one, the entropy of a given region, which counts the information in the region, is finite. It's not infinite. And secondly, it's not volume, but it's area scale. So there are many less quantum states available in a given region than what QFT would have you believe in that sense. So what we were trying to ask is, if this is incompatible with standard quantum field theory, because there is a massive depletion of quantum states coming from these delocalized area scaling laws from gravity, and further, every single region, the number of possibilities are finite. Why? Because if I start to excite different modes, start to add energy, A dagger, A dagger, A dagger, eventually I have so much energy that my region collapses into a black hole. And then the area law starts to work again. Okay. So how do you reconcile the two? So we have been trying over the last few years to use some perspective from quantum information. In quantum information, if you have different registers, different quantum bits, every single quantum bit is independent. I can go and change this quantum bit without changing the other quantum bit. At least I can create such states if I would like. Okay? But what happens is, what if I start to look at something like overlapping qubits, where they are not independent of each other, but they are somewhat dependent and somewhat overlapping. That is to say, in an 8-dimensional space, you could have found 3 independent qubits, right? 2 times 2 times 2. But you might be able to find many, many more overlapping, slightly dependent qubits. So we use this result of quantum information, and it connects back to something very amazing in linear algebra, something called the Johnson-Lindenstrauss lemma, which says that in a d-dimensional vector space, you can actually find exponentially many pairs of vectors which are almost orthogonal, almost perpendicular, but not quite. Right? So in, let's say, 100 dimensions, 100 pairs exist of orthogonality, but you can find either the 100 pairs which are almost orthogonal. It's like an image, it's like a compression algorithm, if you will. So we applied this to gravity in some broad sense. You also expect this lack of independence coming from gravity also. You know why? Because gravity is a universal force. Gravity cannot be shielded. Electricity can be shielded, positive, negative charges. Gravity cannot be shielded. If I put some mass or some energy, its field lines go all the way out to infinity. There's a Gauss's law for that, if you will. Yeah. So gravity cannot be localized. And because of this, you cannot factorize the state, the Hilbert space, into something inside and outside. They are not independent. There is some overlap in between them. So we wanted to basically use this stuff from quantum information and apply it to basic ideas in holography in gravity. So we did this. We ran a simple model where we were trying to compress for each energy, let's say, shell in momentum space, compress it such that the scaling of the degrees of freedom is not volume, but rather is area. And what you find is that every single different quantum harmonic oscillator or quantum mode has a certain overlap between them, which depends on the energy. So we try to build some basic models which can be applied to cosmology, where this principle of area scaling is inbuilt into the quantum theory. Just a glimpse of what we are doing, but just going to put this out there. What you also find out is that as a consequence of this, the 0-point energy is massively suppressed in these things, which might have implications for so-called cosmological constant property. In the universe that we live in, there is a certain amount of dark energy even in vacuum. Our predictions from quantum field theory are actually way above what we actually observe. So maybe because of these holographic overlaps, the energy is actually much more suppressed and is much more closer to what we observe. This is again a basic toolkit right now. We're not close to being done, but we are asking the question, can we question the obvious that has been done for the last many years? Okay. I'm going to maybe go a little faster with this. Okay. The other thing is, what about the finite dimensionality? So we tried to make a simple model where we used a scalar field, a certain quantum field in the universe, which is expanding in the so-called FRW cosmology, Friedman, Robertson, Walker, where you have isotropic and homogeneous expansion. And I tried to ask the question, what happens if we look at finite dimensional oscillators? Okay. So what you have is the Hamiltonian is literally a bunch of independent, free harmonic oscillators with each of its mass and energy becoming time dependent because you have an expanding universe. Okay? So we try to model this. Cosmologically, what would happen is Einstein's equation, Friedman equation, tell me that the energy density coming from the Hamiltonian affects how the universe is expanding in time. Okay. So the question was, if I want to have a finite dimensional approach to my quantum variables, I am going to need a finite dimensional, a matrix representation of a position operator and a momentum operator, which obeys Heisenberg's commutation relationship, right? And that would be a finite dimensional version of quantum mechanics. So the question is, can I find an n by n matrix for position, n by n for momentum, such that their commutation xp minus px is I h bar, for the ones who know physics? The answer is a big fat no. It's something called the Stone-Von-Neumann theorem. I won't go into it right now, but just look at it this way. If I take the trace on both sides, the trace of a product is cyclic. So trace AB is trace BA. So trace on the left-hand side vanishes. But on the right, trace of a number and the identity is not zero. So something fishy is going on here. And there are amazingly beautiful mathematical details about trace class matrices, von Neumann algebras that can be learned. But again, my point here is, even with the basics, a lot can be done. So what we did was, we went back to this paper by Hermann Weyl from 1934. And what Hermann Weyl did was, Hermann Weyl had an exponentiated version of this commutation relationship, where you have translations in position and momentum, where exponentiated versions actually, in the large dimension limit, approaches Heisenberg. And this particular commutation relationship does have representations as n by n matrices. That's how they look like. They're as simple as that. You can go to Python today, open your Anaconda notebooks, you can simply just code up these matrices. These matrices shift you by one or tell you where you are on the basis. That's it. Very, very basic matrices. You might say, this is weird, I don't know what's going on right now. But if you've taken basic quantum mechanics, you have seen this. For n equals 2, these are literally the poly z and the poly x matrix. So spin is actually part of the so-called generalized Clifford algebra. I'm throwing words out that I know, but I want to kind of convince you that there is a lot happening in the basics as well. Okay. Anyways, we applied this to quantum mechanics, to this cosmological model, and we found some amazing details where, again, vacuum energy is massively suppressed from its QFT counterpart. Vacuum energy can actually become dynamical across times. So maybe this is a model where we started with inflation, and after many epochs, we kind of again thermalize into long-term averages where we are expanding again in the universe. So simple matrix models.
Here the green, what does the green, orange, and blue line represent?
So they are different parameters for the model.
Okay.
Yeah, the ND and the D, they are, again, I'm not going into the details here. It's not a research talk per se.
Yeah.
Giving you a flavor of what can be done, but they are parameters of the model. Yeah. And then depending on the equation of state, the so-called ratio of the pressure to the energy density, also something pretty fantastical, something which can be mapped to experiments. Again, going to the basic matrices of what position momentum end up doing. So questioning the basics and looking forward, I'm trying to basically apply this to cosmology a lot more concretely, a lot more quantum information focused. So that's our big goal. Okay, here is a bigger goal. Can we try to basically connect this back with emerging structure in Hilbert space? How does space and time emerge? How is that connected with the so-called holographic effects in cosmology? So we've been looking into some basic questions like how do you even define split in Hilbert space? How do you call something as system and something as environment? What defines this? Because in gravity, locality is very subtle. So we're asking some basic questions from first principle and see what we can do with it. So when I worked on this back in my PhD times, no one really cared about this. It was a paper lost in oblivion. I wrote it. It was one of my main papers, but no one cared about it. It was very disheartening. It was kind of, a little bit of a kick, like what's really going on? But now, 6 years later, I am seeing interest pick up in this subject. People around the globe are now starting to work on this so-called quantum meteorology problem that we coined as a word. So meteorology is a term in set theory which tells me how the parts of a whole connect with the whole. So something that I worked on which was very basic and touching on the fundamentals of quantum theory, which no one cared about back in the day, is getting some interest now. Not enough still, but something is happening. Questioning the basics again. Okay. I will try to change my tone again a little bit over here. And I'm going to kind of get you back out from this this mindset of research being this hard endeavor where a lot has to be put in as effort, something will be done. It's a long road ahead, right? What I've also found is that there is pleasure in physics from a different standpoint also. When I finished my PhD and I was doing my postdoc at NASA JPL, it was a very difficult time for me. For one, I had defended my PhD and I wasn't sure the questions I asked, were they relevant? Because no one cared about them, I cared about them. Secondly, COVID happened. And sitting in isolation, working in theoretical physics can be a little disorienting sometimes. So I was very disenchanted, very disillusioned, almost at the brink of leaving physics. I almost left academia and went into quant finance, to be very honest. But something pulled me back. My love for physics pulled me back. And I ended up joining a small liberal arts college as a faculty member. And there I found my love for teaching all over again. And I realized that in teaching, in discussions, in talking, something beautiful starts to happen. And in those conversations, in those classes, you can really learn a lot, which fuels your passion for the basics. So I've been trying for the last almost 2 years now, to put some ideas on YouTube under my channel of the Scribbled Equation, where I ask basic questions about everyday life and how can we explain them with basic mathematics. Because often our textbooks teach us a lot, but it's so much that we forget what it really means. So can we understand, by just scribbling a few equations, how can the world around us be described? So talking about ideas like, can we model the Pope elections, for example, using the simple Markov chain Monte Carlo method, simple mathematics? Can we understand how to measure the yield of a nuclear blast by looking at 4 pictures from the blast? Basic mathematics, basic physics from your undergrad classes, applying it to something a little bit more real world, a little bit more quirky. And that said, today when I teach at IIT Delhi, my approach has been to try and make physics a little bit more experiential. I want myself and my students to be able to experience physics, not just as equations, not just as an abstract problems, but how it connects with the real world around us. So when you go out there tomorrow, you see a different perspective of what the world really looks like. Yeah. So to kind of wrap it up and take questions after this, I want to leave you with this one little comic from Abstruse Rules. I had this comic up in my Govind Bhavan hostel room also, amongst other comics. So as you can see here, this is young Einstein. Of course, this is not true, it's just a comic version of it. But Linus Pauling said that the best way to have a good idea is to have a lot of ideas. I want to add to this by saying, have many ideas, tinker with the physics, tinker with the science, do it as a community, do it with collaborators, do it with your friends, where you feel that you can actually connect. And trust me, a lot can be done. The road is not easy, but the road at the end of the day might be worth it. So hopefully I've convinced you of some broad lesson that I've learned across my 15 years. I would love to take questions, so thank you for your time, and I'm very happy to.
So you said that the dark energy is suppressed. Like, can you elaborate on that a bit more?
Yeah, so if you take the standard quantum field results, like 1/2 h bar omega for every single quantum harmonic oscillator, and you add them up,
Yeah.
you get about 10 to the 114 joules per meter cube. Okay? And the observed value of vacuum energy is about 10 to the minus 9 joules per meter cube.
Okay.
So there's an order of about 120 difference between the two. So what we're looking at is, can the 0-point energy of harmonic oscillator, which in standard quantum mechanics is like 1/2 h bar omega, can that be reduced as a result of these holographic or these gravity motivated ideas? If it reduces it, it naturally helps solve that problem.
So you coined the term, I guess,
Meteorology, yeah.
Can you explain that?
Yeah, of course. I kind of skip that a little bit in the interest of time. But so usually what people do is, how they understand the emergence of classicality from quantum mechanics is something called decoherence. So what they say is that a particular system, let's say you right now in the audience, if you were a quantum particle, right, and you were in a superposition of being asleep and awake in the dark. Now the photons in the room, when they bounce off of you, those environmental photons, depending on whether you're asleep or whether you're awake, they bounce off differently off of you. So they entangle with you. So you have now branched the universe into two different parts, one where you are awake and the photons have bounced in a certain way, plus where you are asleep and they have bounced in a certain different way. What happens is, these two different environmental states dynamically in time become orthogonal. They become perpendicular. So these two branches of the wave function then decohere. And that's how classicality emerges at some level, they say. So the question is, who decides to split the universe into a system and an environment? In the laboratory, it's obvious. You are looking at a system, everything around it is the environment. But in gravity, when we're not even sure as to what locality means, it's a little bit more subtle. So are there principles in first quantum mechanics where we can understand what part of the Hilbert space should be called system and what might be called environment for classicality to emerge? So we made an algorithm for that, where we talked about how does this parts of the whole connect to the whole, and asking for some basic requirements of classicality, that good classical variables remain robust under evolution, so they don't decohere very fast, and you can predict classical outcomes. By demanding these two regular outcomes from quantum mechanics, we can find out an algorithm for that. So meteorology is literally a program where we are trying to emerge the right split in Hilbert space, the right factors, the right subsystems for which classical dynamics might emerge from.
I think my question is somewhat ironic in nature. I want to ask you about the art of asking the right questions, particularly because I feel that it is often easier to lean on what's already out there because it's comfortable, as opposed to actually going out there and doing something new.
I must concede that as physicists, as teachers, as instructors, as mentors, we often help you solve questions. We don't help you understand what questions to ask sometimes, right? And it's a tricky business of teaching you how to ask the right questions. So my kind of thought is, the more you experience physics by trying it yourself right from the start, and hence I'm saying at your level, early undergrad, don't let the big fancy ideas capture you right now. Let them capture, sure, but go with what excites you, what kind of catches your curiosity, and try it for yourself. Because you have to learn the art of asking questions actually yourself. Your mentors, your teachers will help you, yes, end of the day, you have to follow through. You have to ask what is your question that you want to be looking at. It's not easy. I will completely agree with that. It might sound, it was very smooth for me. It really wasn't. Yeah, but you just try, keep trying. Have many ideas, but follow them through, and that's what helps you understand which ideas are worth following and which are not. People often think a PhD, is all about becoming an expert in a field. In some sense, it is. But a PhD also teaches you what questions to ask because you spent enough time working in a field, understanding both the good and the bad, and that trains that matures you. That can only happen with time and with some pain.
I haven't studied physics in a while, so I'm a little lost throughout the talk. But I noticed a lot of times you connected or you got inspiration from places which are not even remotely related to physics. So, like, how do you realize you have to make the connection, like go out to your own branch, go out to your own field, and look somewhere else?
I don't think you have to do it actively and you have to be at the lookout all the time. I think that is energy probably not well spent. I think this might sound a little romantic in some sense, but you really have to just enjoy it in the moment. Your field that you're trying to do, right? And talking with your friends in a space where discussions can happen freely. Those discussions that you can have with your colleagues, with your professors, with your friends, that is where those ideas, those connections are made. Because in rooms, and I'll be very blunt with you, in big collaboration when you talk to someone, it is so much, it's so polished that you really can't get to the bottom of something and connect the dots. You really have to sit down over a cup of coffee or a chai or something and just talk it out. So this is the right place to start building that habit. And that's where you find the connections. There is no recipe in my mind that you do it and you find the connections. Some things can be done, yes, right? People have made some connections. But the questions that will mean more to you, I think you have to let them come to you, but you have to be open to accepting them. I'm done with this announcement. That's my
Sir, does this approach have any overlap between the Celestial Photography Initiative at PSI?
Yes, so celestial holography, they've been trying to look at a holographic dual for like flat space-time. So what they're trying to find gravity theories which have duals in the quantum field theory world. And that's most wonderfully worked on ATS CFT. And that's worked well, but we don't live in an ATS universe, right? So our approach is actually flipping the table. It's one possibility. This might be wrong. This might not even work out. So I'm not making a claim that what I'm saying is the right way to do physics or to do quantum gravity. But this is one possibly falsifiable way of doing it. There are no direct links with astrography, but the aim is essentially the same. We're building it up from different regions. They assume what space-time is. We want to build space-time from scratch.
So, my question is that physicists in 60s to 80s used to believe that if we are able to combine the gravity with the other unified theory of the weak forces, strong forces, and the electromagnetic forces, the physics would be complete.
Mm-hmm.
Is that the case still? Like, do the physicists still believe that the unification of all the forces would complete the physics in some sense? Because that's what I read in this book by Stephen Hawking, that the idea was during those times. So, is it still the case?
I would say yes and no. So yes, in the sense of, let's say you're talking about charges, right? And if I can tell you what Coulomb's law is, F equals, K Q1 Q2 over R square for electric forces. If I have specified the physical law governing charges, I know the theory, right? I know everything about it, right? So in some sense, my physics is complete. But in complex systems, what kind of features arise from it, they are really challenging problems. So in some sense, if I know quantum gravity and if I know the unification of all forces, physics is complete at a foundational level. But there are so many open questions that actually exist in our everyday life around us, which are emergent, which are complex emergence from the fundamental laws. So knowing Schrodinger equation, knowing the basic wave function is good enough at the most grounded level, but it doesn't answer questions like why you and I are talking today. Can you explain that from the standard model? Probably not, right? So those questions might still exist about the real world, but physics might be complete in a structural sense at least. That's what I would think, unless something else comes up. And data should be your guide. If you find something new, you should follow that and see what comes up in the experiments.
Within your treatment of quantum gravity, you didn't mention the quanta of gravity or gravitons at all. So does that still fit in? How does that work?
We are very far from that.
Okay.
Again, when I'm questioning the obvious, it actually means I've gone back many decades, and I'm not assuming all the machinery of quantum field theory, graviton, spin to particles. I'm not assuming that right now. The hope is I'm taking lessons from what we know and trying to make changes in the fundamental structure such that when this program is complete, that stuff would emerge. Currently, it's like a big ocean of problems, and you're solving different small islands on that ocean. And as the islands grow, hopefully they'll all connect together, and we'll have one big picture of the entire inversion program. But right now, we are in the nascent stages. Nascent stages. There's a long way to go. We're asking very simple questions, basic questions, which have no applications for the next 10 years. But hopefully, gradually, it'll start to build up a more complete picture for that.
So, like you're trying to say that this approach tries to frame gravity as an emergent phenomenon?
As an emergent phenomenon, absolutely. It's emerging from quantum mechanics. For example, some of my tablets have shown that if you take a bunch of quantum degrees of freedom and their entanglement structure, so if you take different particles or different things which are more entangled and put them closer to each other on a manifold, like you basically define distance based on entanglement. So things which are more entangled are closer, less entangled are farther away. You can actually embed into a smooth manifold and emerge some version of space. And perturbations of entanglement start looking like Einstein's equations on that. So that work has started to be done now, and hopefully it will yield something more.
So you said that we are trying to realize the quantum theory. Why is it not that we are trying to quantize the gravitation theory?
No, people are trying it.
So the work is going on in both directions.
In both directions. People have been trying to quantize gravity for the last 60, 70 years now. String theory is a famous approach in that direction. ADS-CFT is one way of trying to do that as well. There have been ample approaches to do so. And they have taught us a lot mathematically and some physics as well. But this is a different approach. So I'm not saying this is the only one or this is the best one. I'm saying this is another one. And I think being good scientists, we can follow all possible lines of inquiry in a falsifiable way and see where this leads us. That's all I can ask for. If it fails, it fails. It will make me a little sad, obviously, yes, but it doesn't, there are other possibilities. Okay. If there are questions, I could say we can meet off offline. That might be a good possibility. Yeah.
How is the physics related to
Okay, so I did not go in quantum finance, so I cannot answer that question exactly, but I can say this. It's all about, as Patra sir was saying, it's all about correlations in the data. And physicists, we love locality. We know that what is happening right here can only depend on its nearby areas. And that has given us a paradigm to understand how dynamics works. F equals ma is a local law. Hamilton's equation, a local law, right? So with those local laws, we have understood how things evolve in time. We have then combined it with statistical mechanics, to be able to get some probabilistic ideas about what might happen. Combine the two together, something which is able to use a structure within data smartly to predict probabilistically what might happen next is gold for the share markets, right? You can actually get that data and find out those little blips around and use that correlation. That's what they're practically doing. So the mathematical foundation, the mathematical structures in theoretical physics are actually amazingly diverse. They also apply to the foundational quantum ideas and the finance also. I don't know more about that. Okay, so let me maybe say this to close up. That it was a difficult talk to give because I wanted to keep it a little personal. Didn't want to make a full research talk out of it as well. But hopefully it kindled some ideas in you, and I'm happy to hang back and take questions because again, I was where you are many years ago. So again, thank you for your time, thank you for having me here, and I wish you all the luck as we proceed forward.